We want to evaluate the given surface integral where the surface S is a helicoid with the vector equation given by r of u comma v, and u is on the closed interval from 0 to 4, and v is on the closed interval from 0 to 2 pi. For a surface S given parametrically, or by a vector valued function r of u comma v as shown here, that is defined over a region R in the UV plane, so the region R will be the projection of r of u comma v onto the UV plane, the surface integral of f of x comma y comma z over the surface S, written as the double integral over the surface S of f of x comma y comma z, integrated with respect to S, is equal to the double integral over the region R of f of u comma v times the magnitude of the partial derivative of r with respect to u crossed with the partial derivative of r with respect to v times differential a. So notice how to evaluate the surface integral. We write f of x comma y comma z as a function of u and v using r of u comma v, and differential s is equal to the magnitude of this cross product, differential a. So going back to our problem, let's first take a look at the surface S in space. So we're integrating the integrand function over this surface, and notice how if we project this onto the UV plane or look down on the UV plane, we can see the region R in the UV plane is this circle centered at the origin with a radius of 4. So over here we have a graph of the region R in the UV plane, which we'll use later to determine the limits of integration. Let's first write the integrand function as a function of u and v. We're looking at r of u comma v, x equals u cosine v, y equals u sine v, and z equals v. So f of u comma v would be the square root of the quantity 1 plus x squared would be the square of u cosine v plus y squared would be the square of u sine v. Let's go ahead and simplify. We'd have 1 plus u squared cosine squared v plus u squared sine squared v. But notice how here if we factor out u squared, we'd have f of u comma v equals the square root of the quantity 1 plus u squared times cosine squared v plus sine squared v. So f of u comma v is just the square root of the quantity 1 plus u squared. Now for our next step, let's go ahead and find the partial derivatives of r with respect to u and v. Let's do this on the next slide. So the partial derivative of r with respect to u would have an x component that's the partial derivative of u cosine v with respect to u, which would be cosine v. The y component is the partial of u sine v with respect to u, which would be sine v. And the z component is the partial of v with respect to u, which would be 0. Now we want to find the partial with respect to v. So the x component is going to be the partial of u cosine v with respect to v, which would be u times negative sine v, or negative u sine v. The y component is the partial of u sine v with respect to v, which would be u cosine v. And the z component is the partial of v with respect to v, which would be 1. So now we want to find the cross product of these two partial derivatives. We'll determine this cross product using a 3 by 3 determinant as shown here, where the first row are the unit vectors I, j, and k, the second row are the components of the partial with respect to u, the third row are the components of the partial with respect to v. Using expansion by minors, for this first 2 by 2 determinant, we eliminate the row 1 column of the I vector, so we'd eliminate row 1, column 1, leaving us with these 4 elements for the first determinant. For the second determinant, remember we have a minus here, and then we eliminate the row 1 column of the j vector, so we eliminate row 1, column 2, leaving us with these 4 elements. And then finally for the last 2 by 2 determinant, we eliminate the row 1 column of the k vector, so we eliminate row 1, column 3, leaving us with these 4 elements. And now we evaluate each 2 by 2 determinant by determining this product minus this product. So for the x component, we have sine v times 1 minus 0. So we have sine v times I, and then we have minus cosine v times 1 minus 0. So we have minus cosine vj, plus for the z component, we have u cosine squared v minus negative u sine squared v, which becomes u cosine squared v plus u sine squared v times k. But again, notice how if we factor out the u here, we have u times the quantity cosine squared v plus sine squared v, which simplifies to just u times 1, which is just u. So in component form, the cross product is angle bracket sine v, comma negative cosine v, comma u, angle bracket. And now we want to find the magnitude of this cross product, which I've also already set up. The magnitude of the cross product is equal to the square root of the square of sine v plus the square of negative cosine v plus u squared. We should recognize this again. Cosine squared v plus sine squared v is equal to 1, and therefore the magnitude of the cross product is equal to the square root of the quantity 1 plus u squared. So going back to our first slide again, the magnitude of the cross product of the partial derivatives equals the square root of the quantity 1 plus u squared. So now we can set up the double integral shown here, where the given surface integral is equal to the double integral over the region R, which we'll come back to, of f of u comma v, which is the square root of the quantity 1 plus u squared, times the magnitude of the cross product, which is also the square root of the quantity 1 plus u squared. And then for differential a, let's use the order of integration du dv. So using the region here, or just the intervals given for u and v, the limits of integration for u are going to be from 0 to 4, because the radius of the circle is 4. And notice how it's also given here. And then to trace out this region in the uv plane, v would have to be from 0 to 2 pi all the way around the circle, which is also given here. Let's go and evaluate this on the next slide. Notice how this product simplifies nicely to 1 plus u squared. So this gives us a double integral of the quantity 1 plus u squared du dv. And now we integrate with respect to u. So we'd have u plus u to the third divided by 3, or 1/3 u to the third. And now we need to find big F of b minus big F of a. So when u is 4, we have 4 plus 1/3 times 4 cubed minus, when u is 0, we have 0 plus 1/3 times 0 to the third. So here we're going to have 4 plus 64 thirds minus 0. 4 plus 64 thirds is equal to 76 thirds. And now we integrate with respect to v, so we have 76 thirds v. Forming substitution, we have 76 thirds times the quantity 2 pi minus 0. So we have 76 thirds times 2 pi, which is equal to 152 thirds pi, which would be the exact value of the surface integral. Or as a decimal approximation, this would be approximately 159.1740. I hope you found this helpful.